We're now going to continue our look at determinants of larger matrices. Right? Now, previously we defined the determinant of an n by n matrix using this cofactor expansion. So let me remind you of that definition. Right? So recall if A is n by n, right, then the determinant of A is defined by this quantity. So you take the entry in the 1, 1 position, so first row, first column, and multiply the corresponding cofactor, and then you add to that the product of A1, 2 and C1, 2, and then you continue that across the entire first row, right? So until you get to A1n, C1n. All right, and we know how to find our cofactors. Those are defined as the signed determinants of certain submatrices when a row and a column is deleted. Right? Now, let me write down a problem, and then like with a specific matrix, and say, well, if we were to use this definition, this is what we would have to do. Right? So let me consider this, and I'll use a 4 by 4 matrix as an example. So the matrix is 1, -2, 3, 0, and then -1, 1, 0, 2, 0, 2, 0, 3, 3, 4, 0, and then -2. All right, so let's say this is our matrix. Now let's write down what this cofactor expansion would be using this first row. So let's go down. So then again, let's write it out symbolically first. So the determinant of this matrix is going to be A11 times C11 plus A12 times C12 plus A13 times C13 plus A14 times C14. All right? So what do we have? We have the 4 numbers that we need. We have the A's, right, because those are entries in our first row, and we have definitions for our cofactors. So let's write it down and see what it looks like. So A11 is 1, right? So let's put a 1 there. Now C11 is going to be, it's that -1 to the power I plus j. So add the I and j values. And then I have to multiply that by the minor, which is the determinant of the submatrix that I get by deleting the first column and the first row. So if I block out the first row, first column, I'm left with this 3 by 3. So then I'll have 1, 0, 2, 2, 0, 3, 4, 0, -2. All right? And then I'd have to add to that, then I have to take the entry in the first row, second column, so that's -2. And then I have to multiply that by, so now it's C12 is -1 to the third power times, and now let's block out the first row, second column. So if I block out the first row, second column, I'm left with -1, 0, 2, 0, 0, 3, 3, 0, -2. And then I have to keep going, so then plus 3 times, and then the same expression, -1. Now I and j are 1 and 3 respectively, so then I add those together. I'll have -1 to the fourth power, and then times. Now block out the first row, third column, so that leaves -1, 1, 2. and then 0, 2, 3, and then 3, 0, negative 2, right? And then the last term now, see, this entry is 0, right? So no matter what the cofactor turns out to be, because that entry is 0, I'll end up adding 0 there. So I'll just put a 0, right? But still, so to evaluate the determinant of this 4 by 4 matrix, I then have to compute the determinant of these smaller 3 by 3 matrices. So then I would have to, do my cofactor expansion again on this, but now I'll have 3 terms, but each of these will be multiplying a 2 by 2 determinant. I mean, and that's what it looks like when you get larger and larger matrices. If you use this definition, it's not the most efficient way, right? It works, but it's very, very tedious. Now, what we're going to do in this video and in a few subsequent videos is look at a few other approaches, right, that can help. Now, the definition requires that we use the entries in the first row to do our expansion, right? Well, it turns out that this definition actually can be extended into a theorem that says you have a choice as far as which row or which column you can use. So in other words, we don't have to use the first row, right? Even though that's how it's defined, there's a theorem that states we can use any row or column to do our expansion, right? And so let me write down the theorem, and then what we will do is come back and apply it to this matrix, right? So here's our theorem. And this theorem is again, it's called the expansion by cofactors. So expansion by cofactors. And it is due to Laplace. I'll put his name there. So Laplace, French mathematician. And he says for any matrix, fix that. So for any matrix A, that's n by n, the determinant of A may be found by using a cofactor expansion cofactor expansion of any row or column. Of any row or column. So what I'm going to do is write down any row or column. I'm going to write down 2 expressions that represent this. So if we are using row I, I'll say the row I expansion would look like this. So it would be AI1 CI1 plus AI2 CI2 and then plus ... You continue until you get to the last entry in that row, which would be AIN CIN. So in our original definition, the i's were all, well, I was equal to 1, and that was row 1. But what Laplace figured out is, hey, you don't have to use row 1. You can use any of the rows, right? Not only that, but you can use any column. So if you were to use column J, this is what the expression would look like. So the determinant of A again, using any column we want, well, we would start in, the first entry in that column. So it would be 1J and then C1J, and then go to the next entry in that column. So that will be A2J, C2J, and then continue all the way down till you get to the bottom of that column, and that would be your A, NJ, C, NJ, right? So this is a big step forward, because the definition that we had, and we saw it in the previous video, it said you have to use the first row in your expansion. And Laplace is saying, whoa, 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 no, you don't. You can actually use any row or any column, and they will all give you the same number, as long as we don't make any arithmetic errors, right? Expanding across any row or any column will give us the same determinant. Now, why is this helpful? Well, let's go back to our original problem. I'm going to rewrite the matrix, right? So remember, this is what, let me put a little line here to say that ends the theorem. So let me go back to our 4x4 matrix, where when we wrote down the process using that first row, it didn't look like fun, because we had so many other 3x3 determinants to compute, and that in general is a problem. But now, armed with what Laplace says, we can look at this matrix and decide, is there a row or column that would be the best choice? So think about what we do when we do our cofactor expansion. We take the entries in a row, and now it could be any row or any column, multiply them by their corresponding cofactors, and add them together. But take a look here at column 3. Column 3 is almost filled with zeros. There's only one non-zero entry in column 3. So if I were to write down what the cofactor expansion is using this column, I would be multiplying by 3 zeros. So 3 terms in that cofactor expansion would cancel out. That means it would be a lot easier for me to work with, right? So I look at this, and what this theorem allows us to do is now choose wisely. And one of the obvious ways to choose is to choose a row or column that has the most number of zeros. Now, if you have a few of them that have the same number of zeros, then again, it doesn't really matter, but you'd want to choose at least one that has the most numbers, right? So what this theorem is saying, as a guide, when you're doing the cofactor expansion, right? So perform the cofactor expansion using a row or column with the most zero entries. With the most zero entries. It's like we love seeing zeros in matrices. They make a lot of things easier. Okay, so now let's revisit this problem and see if we can actually compute the determinant. So what does Mr. Laplace say? Pick column 3. So I'm just going to put in parentheses down here that we're using column 3. Right, so using column 3. Well, again, let me write it out symbolically. So column 3 will consist of these entries in this order. It will be A13, and then I'd have to multiply it by C13. Then I will have A23 times C23 plus A33 times C33, and then finally A3, 4 times C3, 4, right? So these are the A's are the numbers that I have here highlighted in red. And then we haven't found the cofactors yet, but look at what happens if I simply just substitute the numbers in. So the 3 goes here, and then this 0 goes here, and then this 0 goes there, and then this 0 goes there. So even though I haven't computed those, the C23, the C33, the C34, it doesn't matter what those numbers are because they're going to be multiplied by 0, right? So I'm going to have 3 times C13. Again, let me write it in for emphasis. You're going to have 0 times C23 plus 0 times C33 plus 0 times C34. So no matter what those C's are, since I'm multiplying by 0, they all go away. So expanding using the third column just means I have one cofactor to compute, at least one of these. Now, again, we're going to have to continue breaking it down until we get to a relatively, or to a point where we can use the formula for the 2 by 2s, but let's see what it looks like. So we have 3 times, then I have -1 raised to the power 4, right? I plus j. And then let's write down what the minor will be. The minor of the 1, 3 entry is going to be the determinant of the 3 by 3 matrix that's left after I delete the first row, third column, right? So first row, gone. Third column, gone. And what's left is, so let's write down those remaining 9 entries. So we have -1, and then 1, and then 2, and then 0, 2, 3, and then 3, 4, -2. All right? Okay, so what we've done, we've written down the expression for the determinant of this 4 by 4 matrix. We made a good choice because it eliminated all but one of the terms, right? And then, so what we're left with now is the determinant of this 3 by 3. So we're going to have to do the process again. We're going to have to make a choice as far as, choosing a good row or column where, if you have a 0, you're going to want to use that row or column. Now, this coefficient here simplifies to 3. Now, what I'm going to look at this and say, I see this 3 by 3 determinant has one entry that's 0. So I can choose to use either the second row or the first column. It's going to amount to be the same, right? Now, we started by doing the third column. Let's switch it up and do a row now. So let's say I'm going to write down the determinant of this now using the second row, right? So I'm going to maybe put this over here. So we're going to use this row. So using the second row, right? So let's write down what that would be. So it's going to be, now I'm looking at this, right? I'm looking at this. I'm not referring to the original matrix because we've already expanded that determinant and we've brought it down to this point. Now to evaluate this determinant, we repeat the process. So let me write down the expression for the second row expansion here. It's going to be A21 C21 plus A22 C22 plus A23 C23, right? And all of that is going to be multiplied by 3. All right? Now, we have a 0 entry there, right? So this first term is going to be 0. So I'll write it in. So it's going to be 0 plus, now A22 is that entry right in the middle, second row, second column. So it's 2 times. Now let's write down the cofactor for the 2, 2 entry of this 3 by 3 matrix. So by definition, it's negative 1 to the power 2 plus 2, so that's 4. And then I have to delete the second row, second column, and find the determinant of the submatrix that remains. So if I delete the middle row and the middle column, I'm left with negative 1, 2, 3, negative 2. So let's write that smaller determinant down. So negative 1, 2, 3, negative 2. And when we get down to a 2 by 2, that should make us happy because we know a formula for computing the 2 by 2 determinant, right? So we know we're nearing the end. And then the A23 entry is 3, so it's going to be plus 3 times, and then it's negative 1 to the power 2 plus 3, so negative 1 to the 5th power. Now block out the second row, third column, so blocking out the middle row and the last column leaves the entries negative 1, 1, 3, and 4. So I have negative 1, 1, 3, 4, and then I'll close my parentheses, right? So again, before we write down the final number, because we're at the point now where all the heavy lifting is done, but if you notice what we had to do, we started with a 4 by 4 matrix, and this was its a cofactor expansion. But we kind of lucked out because so many of the entries were 0, so it eliminated a lot of these. But we were still left with a 3 by 3 determinant right here, right? Because this is one of the cofactors. Right? So then we had to expand this one, and again we had a choice which row or column to use. Always look for entries that have, that are 0, and then think about using that row or column. Right? And then we broke those down, and we're now at a point where the determinants that are left in my expansion are all 2 by 2, so we can use our AD minus BC calculation. Right? So let's do that to finish it up and see what the magical number is going to be like. So we're going to get a number, and it's like, man, that's a lot of work for a number, but that's how it goes. All right, so I won't write the 0, and then we have 2 times a positive 1, so that's 2, and then let's write down our 2 by 2 determinant. So it's negative 1 times negative 2, so that's 2, minus 2 times 3, so that's 6. And then now 3 times negative 1, so that's minus 3 times, and again, another 2 by 2 determinant. So this is negative 4, and then minus 3. And there we go. So again, we have just be careful with our order of operations. Let's see what we have. So we have the 3, that's going to be multiplying. Now we have, in parentheses, this is negative 4 times 2, so that's negative 8. And then here we have negative 7, right, times a negative 3, so that's negative 20, oh, I'm sorry, positive 21. There we go. And then finally 3 times, now this is 13, and then we end up with 39. So that's our determinant, right? So again, computing determinants using the cofactor expansion is not for the faint of heart. You have to love arithmetic. It's a lot of breaking things down step by step until you get to the 2 by 2 determinants, and then we use our 2 by 2 definition, right? Now, this is not the only way to compute a determinant. In fact, we've seen by this particular example, let me go back up just to have it on the screen as I talk about it. We see that the having zeros strategically placed in your matrix is a huge benefit, right? So What if, like, if we start with the matrix that doesn't have zeros at all, and let's say we were to use our row operations to create entries that are zero, right? So what if we eliminated some of the entries? How would that affect the determinant? So if we can answer that question, we could then combine what we know about our row operations with this process of computing determinants with the hopes of making it a lot more efficient, right? And that's what we're going to do in the next video. So if you're just dying to see that process, why not hop on over right now? See you then.